Hello friends, welcome to Physics with Ben. Don't forget to subscribe, like, comment and share this video. You may also love to turn on the notification bell so that anytime I upload a new content like this, you will be duly notified. Also, click in the description box below to find all the video links on physics mechanics experiments. In today's video, I want us to look at the experiment before you. We want to perform simple harmonic motion using the meter rule, the slotted masses, the G-clamp, and the stopwatch. Without wasting much time, let us go straight to the business of the day. This is the experiment I want us to perform today. It is a WAEC pass question. But these questions are very, very important when it comes to preparation for your exams. So let's read together. You are provided with a meter rule, a G-clamp, and a set of masses. Clamp the meter rule to the edge of the bench such that 90 cm of the rule projects from the edge as shown in the diagram above. Ensure that the rule is capable of performing oscillatory motion. Fix a mass m equals to 50 grams at the free end of the rule. Deflect the rule slightly such that it performs vertical oscillations. Determine the time t for 10 complete oscillations. Calculate the period t of the oscillations and evaluate t squared. Repeat the procedure for 4 other values of m is equal to 100, 150, 200, and 250 grams. In each case, determine and record the corresponding values of t, time t, period capital T, and period square capital T square. Tabulate your readings. Plot a graph of t square on the vertical axis and m on the horizontal axis. Starting both axes from the origin 0, 0. Determine the slope s of the graph and its intercept c on the vertical axis. Evaluate k is equal to 4 pi over s, taking pi to be equal to 22 all over 7. From your graph, determine the period t when mass is equal to 180 grams. State 2 precautions taken to ensure accurate results. BI. Explain simple harmonic motion. BII. Define period and frequency with respect to a simple harmonic motion. You may love to screenshot this. So without wasting more time, let us go straight to the business of the day. The examiners asked us to fix our G-clamp. These are the things we need. The G-clamp has already been fixed here. The meter rule, 10 cm is inside, and from this point to this end is 90 cm. That is what we have done. What I'm trying to say is that the whole of this is inside, while this is at the edge of the tip edge of the bench. And so from here to here is 90 cm. That is what we have done. This is the position of the G-clamp. This one is downward and this one is up. That is what we have done here. And so for this particular experiment, we need 50 grams, and then we need 2 100 grams. These are the slotted masses we need in the experiment, and then we need a masking tape so that we can staple it at the edge of the ruler here. So these are the things we need. So next up, we are going to do the first things first in every experiment as usual. What is that? The table of values. I believe we don't have issues generating the table of values. Do we? We don't. So you observe that I highlighted some points when I was reading. Those points I highlighted are the areas where we have to lay much emphasis while generating our table of values. Yeah. You see that I highlighted M here, small t here, capital T here, T square is there, M is there, and then small t, capital T, and then capital T square. Those are the composite parameters we must include on our table of values. So let's generate our table of values. Behold our table of values. So the next thing we are going to do is to start performing the experiments. So we are going to fix the 50 gram mass at the end of this rule here. And then we're going to use this masking tape and sellotape it. Good. Before we do that, observe something quick. In this experiment, I always tell us about the relationship quantities have with each other in physics. The increase in the mass that will be hung or that will be taped on this ruler will be inversely proportional to the frequency. If you observe that there's no mass, this meter will oscillate very fast. And the more we increase the masses, the slower the meter rule will oscillate. Observe that. You see that? Good. So we are going to fix this here, and the mass that will be attached here will be inversely proportional to the frequency, while it will be directly proportional to the period, I suppose. Let's try and see what will happen. So right now my stopwatch is on 0, 0. We are going to oscillate it. It will go up and come down. That is one oscillation. And that one oscillation is equivalent to 2 pi in radians, which is the same thing as 360 degrees. It will go up and come down. That is one oscillation. So let's begin our experiments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 5.22 seconds. 5.22 seconds. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 4.59 seconds for the last time. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is actually the result. 4.59 seconds is the result. So I record 4.59 seconds there. The next is 100. I will detach this and attach 100 to it. So we attach 100 to this end. Good. We are good to go. So we reset our stopwatch back to 0, 0. Are we good to go? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 6.22. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 5.85. One, two, three, 4, 5, 6, 7, 8, 9, 10. And so we go with 5.88. I'm supposed to have T1, T2, and then average T here, but I don't want to do that. I don't want to make this steady. This is okay. This value appeared almost twice, so we'll go with 5.88. So I record 5.88. The next, we are going for 150. We'll add 50 to this. So we're going to add 150 together and attach them together. The meter rule you are supposed to use must be capable of performing simple harmonic motion. And the one I'm using here is just good for this job. Good. The load is increasing at this end. So we are good to go. We reset our stopwatch. Are we good? Yes, we're good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 6.71 seconds. Let's start it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 6.85 for the last time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 6.81. So the answer is actually around 6 point something. So this is 6.81 seconds. The next is 200. We're going to remove this and add this to this. So this is 100, 100, 200. Load is increasing. You observe that the frequency with which it is vibrating is decreasing. These are the things you note when you are performing experiments. The frequency is decreasing while the period of oscillation is increasing. So the mass and the frequency they have, let me just write something here. The mass is inversely proportional to the frequency. That is one of the equations. You can call this your equation number 1. And then the mass is directly proportional to the period of oscillation. You can call that equation number 2. So these are the two basic equations that are controlling this particular experiment. So increase in the masses will cause the frequency to decrease, and decrease in the masses will cause the frequency to increase. How fast this will oscillate. Increase in the mass will cause the period to increase. So you see the masses are increasing down, the time is also increasing down. We'll get to the period very soon. So let's go. We reset our stopwatch back to 00. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I love this. 7.66 seconds. Okay, 7.66 seconds. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 7.53 seconds. The last time, this one is 7.53. I don't want to take any average. Just pick just one of the values and then we'll keep going. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 7.47 seconds. I'm gonna pick 7.53. So the answer is a 7 points. I'll pick one of that. I don't want to find the average. I would have created a column for that. 7.53. And then pick 7.53. Good. So we're almost done with the experiment. This time we're going to add this to this. And so there's no need taking it up. This is 100, 100, and this is 50. That is 250. So just tap it up here, and then we tape it. Good. You have to make it firm so that it does not fly off during the oscillatory motion. Good. Wow, this is heavy. I'm afraid the ruler will break. Wow. You can see how the effect of gravity on the ruler now, okay? Let's reset our stopwatch. Are we good to go? Yes, we are good to go. I will displace it gently so I don't break my ruler. Okay? To be so sluggish this moment. I'm afraid to displace this thing right now. Okay, 1, 2, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 8.25. Okay, let's do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 8.10 for the last time. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 8.22. I think I go with this. So this is 8.22. And we are done with the experiment. Next up, we are going to finish up our table of values. How do we get this? This time divided by 10 will give you the period. So the first one, we have 4.5. 0.59 divided by 10. We have 0.459. We record it to 2 decimal places. That is 0.46. So this is 0.46. So 0.46 square. 0.46 square. We got 0.2116. We record this one to 3 decimal places each. So record 0.212. So this is 0.21212. Good. And so we repeat the procedure for everything. So we are done with our table of values. Impressive. So interpretation. The trend of the experiment is as follows. The trend is increase, 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 increase. This is the trend. So if we're gonna plot a graph with this particular trend, and we were asked to plot a graph of what in the experiment. If we're gonna plot the graph of this against this or this against this, you can see here it's also increase, increase, 0.2 to 0.6. So since it is increase, increase, our graph will be in this form. I always predict our graph before we plot. Any of the graph we intend to plot, this against this or this against this, this against this or this against this will be the graph. Any of this one. The first graph, the second graph, or the third graph. The first graph with y is equals to mx plus c. The second graph, y is equals to mx with no intercept passing through the origin. And then the third graph, y is equals to mx plus negative c. So these are the 2 types of graph, the 3 types of graph we definitely have when we plot this. So the next thing we are going to do is to use this table of values and plot our graph. Stay tuned and watch to the end. Don't forget to subscribe, like, comment, and share. Also, turn on the notification bell. Thank you. So, welcome back to our experiment. This time we want to plot the graph. The examiners asked us to plot the graph of t squared on the vertical axis and m on the horizontal axis. So this will be on the y and m would be on the x axis. Good. The next thing we are going to do is to find the suitable scale for the graph. Let's choose a scale for this first. This on the vertical axis. This graph is very simple. 0.2, 0.3, 0.4, 0.5, 0.6. You can even predict it before I say it. What do you think will be the scale? So let's write. Write the scale right here so that the examiners will see it. On the t square axis, let's say 2 cm to equals to 0.1 units. 2 cm equals to 0.1 units. On the m axis, we say, we mean this is the WAEC standard graph. So when we say it's 2 cm, we mean 10 small boxes equals to 2 cm. So this is 2 cm, 2 cm, 2 cm. So 2 of this is equals to 0.1. As you move 2 again, you add 0.1 to that's the meaning of 2 cm to 0.1 units. On the horizontal axis, which is the M axis, we say the highest point is 250, the lowest point is 50. That is, these are the two things you consider when you are choosing your scale. You consider the highest point and the lowest point. Can they be accommodated within the range of your graph? And within the type of scale you are using, will they be accommodated? So we say that for this 4 cm to represent 50 units. Good. So we are free to draw this particular line here. Draw it up. I always use pen because I am teaching. Always use pencil for your own end. So your arrow up here, and that is a t squared. Label it correctly, t squared slash s squared. If you don't label your axis correctly, the examiners will fail you. So we want to start our graph from here up, meaning 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. If we draw this horizontal line down here, our graph will stop here, which is not too wonderful. The examiners may not be happy with us. So let's count this so that our graph will occupy everything. So we draw this line. This is our horizontal line. Good. And then the examiners ask us to start our graph from the origin. Starting from the origin, 0, 0. You can see that from there. So right here, 0, 0. That is the origin of our graph, this particular point here, 0, 0. And then we'll put our arrow here to indicate the horizontal axis. And then here we'll write our M slash ground. So this is this point, this is 0, 0.1, this is 0.2, 0.3, 0.4, 0.5, 0.6. Zero 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. So we are done representing all of these values right now. So the next thing to do, let's put this one as well. This one is this is 50. We said 4 cm. This is 2 cm. This is 4 cm. So this is 50. This is 100. This is 150. This is 200. And this is 250. Good. So the next thing to do is to find the value for each small box. So for the horizontal axis, 50 divided by, this is 10, this is 20. 50 divided by 20, 50 by 20, we have 2.5. 50 by 20, we have 2.5. So 2.5 is the value for each small box on this axis. Here, 0.1 divided by 10. 0.1 divided by 10, we got 0.01. So we say 0.1 divided by 10, the answer is 0.01. Always do this in all the graphs you are plotting. It will help you so much when you want to include values like this. So you're going to divide every value here, especially these values, by 0.01. As we have been doing in all my experiments, that is what we are going to do here today. So let's plot the first point. When the mass was 50 here, what was this? The square of the period, 0.212. So how do we get 0.212 on the graph here? Precisely, divide this by 0.01. So we say 0.212 divided by 0.01. That will give us 21.2. We round it down, meaning 21 small boxes. We count up 21 small boxes beginning from here. So this is 10, this is 20, and this is 21. Let's count. This is 10, this is 20, and this is 21. So this is where 50 and 21 are meeting. This is where we can find 0.212. The next point, when the mass was 100, what was the period? It was 0.348. So say 0.348 divide by 0.01. 0.348 divided by 0.01. We got 34.8. We round it up, that is 35. So we count 35 small boxes. 35 small boxes. So this is 10, 20, 10, 20, 30. 1, 2, 3, 4, 5. This is the point. Good. So we do that for the rest of the values. What a perfect graph. So we are done with the graph. So the next thing is to draw our line of best fit. So I have touched 3 points. 1 point is above the line and 1 point is below the line. Very good. This is wrong. You can't draw a line like this. This is wrong. This is this could also be correct, but your line must touch at least 3 points. So this is also wrong. You can't go with this. So do touch 1, 2 below, 2 above the line. So let's go with, you can also go with this. So let's go with this 3 point here. We touch this point, and this point. So don't forget, we have 1, 2, 3, 4, 5. We also have 1, 2, 3, 4, 5. Your plotted points must correspond with what you have on the values, on the table of values here. So we draw this line. Above the line, below the line. So let's draw this. Good. This is our graph. So the next thing we do is to draw our triangle. Our triangle, we can pick this point. So let's pick this point, although it is falling on a plotted point, but it is not a hand. Let's pick this point. It is not always like that. Pick this point, this and this. Then we pick this point here. This will give us. So we draw this line. We join it. Then down here, dotted line, dot. You draw this one. Take a continuous line. And then dot. Good. Then you trace this point here. Dot. Here becomes your M2. Here becomes your M1. You also trace this point. So here becomes your T square 2, and here becomes your T square 1. And this is your change in T square, and this is your change in M. So you may love to screenshot. Good. So the next thing is to find the slope for the graph. The slope for the graph is given to be change in T square over change in M, which means T square 2 minus T square 1 divided by M2 minus M1. From the graph, our T square 2 is what? We use the value for each small box. That is 0.01 times. This is 10. 0.01 times. This is 10, 20, 30, 40, 50. 50, 1, 2, 3, 4, 5, 6 times 56. That's the value for T square 2. So our T square 2 is 0.56 minus exactly 0.2. T square 1 is 0.2 minus 0.2 divided by the value for each small box here was 2.1. So I'm sorry, 2.5. So our M2 is directly on 200. So this is 200 minus 2.5 times. This is 10, 11, 12 times 12. That is 30 minus 30. And so 0.36, this minus, we got this 0.36 minus divided by this, we have this is 0.0021118 second square per gram. Therefore, our slope is equals to that. The examiners ask us to do what? To plot the graph of this, determine We want to determine the slope of the graph and the intercept. The intercept, we are done with the slope. The intercept, change in C. The intercept is gotten is from this is the intercept at this particular point here. So we say change in C indicated on the graph. Good. So how do we get the intercept? 0.01, the value for each small box, 0.01 times, this is 10, 1, 2, 3, 4 times 14 times 14. So our intercept on the graph is 0.14 second square. That is our intercept on the graph. That is how we got it. Good. So the next thing the examiners ask us to do is they ask us to evaluate K is equals to 4 pi over s, and that pi equals to 2 over 7. So this implies this s is actually our slope. This s is the same thing as our slope. So this implies that our k is equals to 4 times 2 over 7 divided by the slope, the value of the slope, 0.002118 second square per gram. And so that got this to this point. We have 5,935.520. What's the unit? You have -2 this, or you can say that this is something as 5,935.520 gram. Therefore, K is that. Next up, the examiners ask us to, from your graph, determine the period T when M is equal to 180. How do we do that? This is the graph, and we said that this is the mass. The value for each small box here is 2.5. So how can we get 180? I think 2.5 times 72 will give us 180. So this is 10, 20, 30, 40, 50, 60, 70, 71, 72. This is exactly where we can find 180. So our 180 gram is here when mass is equal to this. So we trace this point, and where it touches the line of best fit, that is the value. This is it. You have to indicate it so that the examiners will know that you know what you are doing. So this is the point. So you trace this point back to this. Good. And so your period, your t square here at this point here is what? How do we get that? 0.01 is the value for each small box in the vertical axis. So 0.01 times, let's count. This is 10, 20, 30, 40, 50. 1, 2, 52 times 52. So t square here is 0.52. So what we are trying to say is that when mass was equal to 180 gram, t square was equal to 0.52 seconds square. But unfortunately, we are not looking for t square, we are looking for t. So you have t square times 1/2 is equal to 0.52 seconds square 1/2. So that our t becomes the root of 0.52. The root of 0.52 is what? Root 0.52 will give us 0.7211 second. So this is what the examiners are asking us to do. Get it? Good. Good. Take a close look at it. So the next thing the examiners ask us to do, they ask us to state 2 precautions. So precaution number 1, I ensured that the meter rule was firmly clamped. If the meter rule was not clamped properly, it will fall apart and then you will not draw the experiment successfully. Readings were repeated. You saw me repeating those readings to get my average T, but I didn't record the average T on the table, so I repeated the reading to get accurate result. I ensured that the meter rule was firmly clamped. And then number 3, you have to state 2. I avoided error, parallax error when reading the stopwatch or the stop clock. We stop at that. So the next thing the examiners ask us to do is they ask us to explain what we mean by simple harmonic motion. Simple harmonic motion is defined as the periodic motion of a body or a particle along a straight line such that the acceleration of the body is directed toward a fixed point, and it is also proportional to its displacement from that point. The next thing the examiners ask us to do is they ask us to define period and frequency of oscillation. In simple terms, the period of oscillation is defined as the time taken to make one complete oscillation in the units of seconds. That's the period of oscillation. So the frequency of oscillation is defined as the number of oscillation per unit time in the units of hertz. This is the end of this particular experiment. See you next in another experiment. Don't forget to subscribe, like, comment, and share this video. In summary, this was our table of values, and this was our graph, and then our deductions. Bye bye.